Thank you. Thank you very much. So good morning, everyone. I would like to thank the organizer for giving me the opportunity of giving this talk, although it's probably the topic is a bit different from what we have seen up to now. First of all, do you see the pointer also? Can you?
Yes.
Perfect. Okay, so we can start. So the topic of my presentation is relativistic viscous fluids. So first of all, in a nutshell, what is a viscous fluid? Basically, a viscous fluid is what you get when you remove the assumption that your little volume elements of the fluid are in local thermodynamic equilibrium. So in essence, equilibrium thermodynamics is no more enough to force and describe all the structure of the stress energy tensor, but you open the possibility for much more complicated structures. So suddenly you can have shear stresses, you can have flux of heat even in the rest, flux of energy even in the rest frame of the fluid, and this is what you call heat. And you don't even have any more a clear notion of equation of state in principle. Everything becomes free. Now, while in Newtonian physics, everything is simple because basically there is general consensus on the idea that the best theory is Navier-Stokes. In relativistic hydrodynamics, it's more complicated. You have a whole landscape of many different alternative theories, and it's pretty hard to decide which one is the best. So in this talk, I will not focus on a specific theory. I will let this possibility free. But instead, I will say, let's imagine that we are a research group all together, and we want to create our personal theory for viscous fluids in relativity. So now the question is, what is the most important feature we need to guarantee if we want our theory to make physical sense in the end? Well, take the simplest example possible. Take a glass of water prepared like this, and you have put a vortex in the middle. So this is clearly what we say to be an out of equilibrium configuration. Here, all the complexity of hydrodynamics is evident. You will have probably shear stresses. It's basically an unexplored land. Everything is complicated. And so you will have a stress energy tensor with all these features. But if you wait long enough, after a while, you will get a configuration that's somehow like this. Now, this state can be described using conventional statistical example of equilibrium statistical mechanics. And if you do all the calculations, you will immediately discover that, for example, it's necessary to have a isotropic stress, and that this stress coincides with the thermodynamic pressure. So in the equilibrium states, all this complex structure needs to reduce to the perfect fluid structure. A viscous fluid is indistinguishable from a perfect fluid in an equilibrium state. So this is the first feature you need to guarantee. But there is actually more. Because as I said, if you prepare the glass of water with the vortex, after a while you go here. But the reversed process must not happen. If you start in equilibrium, you don't see vortices spontaneously pop up inside your glass of water. So somehow you need to guarantee that while this process is allowed, this other one is not. If you put this statement in mathematical terms, this is a stability requirement. You want the equilibrium state to be stable against perturbation, or any perturbation, you want it to decay and not to grow. Now, it turns out that while in Newtonian physics, this is quite easy to guarantee. In Newtonian physics, you just you make all the calculations with Navier-Stokes, and you get positive specific heat, speed of some square positive viscosity coefficient. Everything is well understood. But if you move to relativity, everything is more complicated. If you take the straightforward generalization of Navier-Stokes to relativity, basically what you obtain if you just promote J to nu everywhere, then you get the theories of Eckart and Landau-Lifshitz, and you discover that they are unstable. If instead you add more elements here and there, and you create something like Israel-Stewart, and you try to make the theory hyperbolic and so on, then you manage to make it stable, but the meaning of the stability conditions that you get is really hard to understand. You have in front of them, they look completely mathematical, and you don't get what is happening. So answering what is happening here was the main goal of our research. This is what we studied. And we started with the simplest question possible, a very physical question. And the question is, why don't we see vortices spontaneously pop up in a glass of water? Why don't we see it in nature? Well, if you open a good book of thermodynamics, you find the answer. And the answer is quite simple. So basically, the idea is that you have a function that you call entropy. Then you define the equilibrium state, the thermodynamic equilibrium, as the maximum of this function. You assume that it always exists. Now, if you don't have broken symmetries or these complicated things, but you assume to work with a simple fluid, you can also guarantee that the absolute maximum is achieved only here. So you have only one point in which the entropy is maximum. And then you have the second law that tells you that the entropy can only increase, it cannot decrease. So if you combine all these three statements, you realize that these are just the hypotheses of Lyapunov stability theorem. And so you can conclude that the entropy is Lyapunov function of the system and that the thermodynamic equilibrium state must be Lyapunov stable. Lyapunov stable just means that you start close enough to the maximum, you stay close enough to the maximum. And the intuitive explanation is clear. If you want to move away from the thermodynamic equilibrium, you need to reduce the entropy, but this cannot happen. And this is just the mathematical reformulation of the Gibbs stability criterion. So the question is, what happens in relativistic hydrodynamics? So first of all, how do we define the entropy? The entropy is defined typically through an entropy current. The entropy is constructed as the associated charge to this current. And then the second law of thermodynamics is imposed in a divergence form in this way. Now, apart from one theory that I will not discuss here, this condition is always ensured as an exact condition, and this is fundamental. If you really want the Lyapunov stability theorem to apply, you need this condition to be exact. And then if you assume your space-time to be sufficiently simple, you have a finite system and you take two hypersurfaces, one in the future of the other, you can use Gauss theorem and you will get that from this follows that the entropy grows. So our theories, all the theories that we are going to analyze satisfy this condition. Therefore, if we have instability, something here must be broken. So what we just did was to take all the most important theories around, study the structure of the entropy, and see what happens. And indeed, what we discovered is that what actually is broken is the condition that the equilibrium is the maximum of the entropy. And here we come to the most important slide of the talk. If you want to remember something, I ask you to remember this. So the idea is the following. Here you have all the unstable theories. Here you have the stable theories. This is a plot of the entropy. The green dot here is what you assume to be the equilibrium state. Now, the blue line here are those states that have a Newtonian analog. So those states that you are able to take the Navier-Stokes equation, solve them, and you get solution that you can see in parallel to this. While you see there is a new axis, and so a bunch of new states. All these states are states that are strictly impossible in Newtonian physics. There's something completely new that was not conceivable if you use just Navier-Stokes. And what you discover is that in these new states, the unstable theories have the property that the entropy grows along these states. So if you move slightly out of equilibrium, since the entropy can only grow, the system will escape in this direction. And so in the end, basically, I just want to give you an intuition of what these states are, just to understand what is happening. So you take water, take the ocean. Imagine that some heat goes to the left. Now, in relativity, you know that energy flux is equal to momentum density, and therefore you know that if you want the total momentum to be conserved, the fluid must accelerate in the opposite direction to conserve the total momentum. But if you do all the calculation, you discover that in the stable theories, the entropy grows in this configuration. So the system cannot go back to the initial state in which it was at rest, because this would reduce the entropy. Instead, the entropy will keep growing. And so the speed keeps increasing. The fluid starts rocketing, using heat as a rocket fuel in the opposite direction. And this is what drives the instability. So this kind of stuff is not possible in Newtonian physics, as you can see, because it's something that happens only because momentum and because heat carries momentum. So with this, I can conclude. And the main message of the presentation is that be careful when you build your entropy, because thermodynamics always wins. Thank you.
Thank you very much for this concise talk. And since we are now back on schedule, actually, we have time for some questions. So please. Okay, any comments? So maybe
I can ask a question from a partial differential equations perspective. So
Yes.
if you want to solve partial differential equation, it's good to have energy because it controls the solution as it evolves. And then if you study some systems, it's there's this notion of entropy solutions where you have many solutions. The entropy allows you to pick up the best one. So if you take theories of the kind you're doing here, would any of this still apply? Have you ever thought about how this could fit with PDEs and
no, yes, okay. So first of all, the idea of energy, here you have even more, because you have energy and momentum, you have all the constants of motion of the system, and all this state space that I'm showing here in this picture, we are already restricting our attention to state with given energy and momentum. So you take all the possible configuration of the fluid, you restrict our attention to those that are dynamically accessible. So you are at fixed energy, fixed momentum, fixed particle number. You fix all the possible constants of motion that you have, and then you solve everything in this space. So these are plots in this context. Of course, if you let the energy be free also to change, then everything becomes different. But all these arguments are now you can also see the parallel in PDEs. For example, I can give you an element. If you take, for example, the equation of the bulk viscosity. Bulk viscosity tells you that the bulk stress is proportional to the divergence of the velocity. Now, if you move to relativity, the divergence of the velocity becomes the fourth divergence, and you get a time derivative. But then when you go to when you put it in the divergence of the stress energy tensor, then you get another derivative. So the Navier-Stokes equations are of the first order in time, but naturally, when you move to relativity, you get second order in time. And this is what creates this new axis, actually, from the point of view of PDEs. So all these new states exist because you go up of one order in the partial differential equations due to the fact that you have symmetry between time and space. So Navier-Stokes is first order in time, second order in space, but then you mix them and you get second order also in time. And this is what creates new axes. So you can also look at it from the point of view of partial differential equations, and you can also read all this problem of stability in terms of well-posedness, although we didn't go in this direction. There are some papers that before were analyzing it in terms of well-posedness of your initial value problem.
Thank you.
Okay. Further comments or questions?
Yep.
Okay.
So all these viscous fluid theories, they have a problem with relativity to begin with, right? I mean, as far as I'm aware, all of them have sort of a length scale built in, and so there's this whole question of domain of validity of these theories to begin with, because obviously, if one observer formulates the theory, a strongly boosted observer would not agree that certain length scales are small and that the theory is valid to begin with.
I understand, yes.
How does this consideration on thermodynamics play into this sort of domain of validity of the theories sort of considerations?
Well, actually, this is an interesting question. So typically, when one works making hydrodynamics model, they have in their mind the reference of the kinetic theory. And kinetic theory might have, in principle, these issues too, right? Because when you define your distribution function for the particles, it's actually something that you define in the point. But you don't have big issues. I mean, I understand that there is this problem of length scales, but I don't. If you ask me like this, I'm not able to imagine how this should reflect in the mathematics of this problem. So I'm not sure of what you have in mind.
I mean, as far as I understand it, that's also, I mean, that's part of the issue why there are so many different formulations also of relativistic viscous fluid theory, because sort of how to take account of this sort of minimal length scales is, there's a non-unique way how to do this, as far as I understand.
No, actually, the problem is that you want to have hydrodynamics emerge when you take kinetic theory and somehow you reduce your degrees of freedom, because kinetic theory has all the degrees of freedom of a function that lives in a 7-dimensional space, while you want to have hydrodynamics, which you just want to be a field theory, basically. And, you know, once you assume that you are already at the level of kinetic theory, this problem of length scales has already been removed.
Okay.
So the problem is to move from kinetic theory to hydrodynamics. But once you are already a kinetic theory, somehow you can already forget about the problem of the length scale.
Okay,
I'm not sure if...
understand it, but yeah, I don't fully understand that, but I guess I'll take that as an answer.
Okay, in real life, I would say, okay, maybe the two gentlemen could discuss this in private. In principle, you could do this, I mean, on a private channel. Thank you. So if there are no further questions or comments, I would like to thank all the speakers of this morning session. Thank you for your participation and your contribution. And I would like also to thank all the participants for attending and asking questions. And in particular, I would like to thank Thomas Mieling for being such a great technical operator and making all these possibilities working so smoothly. And yeah, finally, I have to say we are now off for the lunch break, and we will reconvene at 2 o'clock.